Happy Tuesday, everyone. Hope that you're having a great day. Hope that your Tuesday goes well. Sorry that I'm not here. Wish I could be in two places at once, but that's not possible. Anyways, I want to work through every other one just to kind of go through the process, just to make sure you guys did well with this. And then the note sheet is either in your hand, stapled to the homework for tonight, which we're not going to do all of those, so hold off on starting that when we start going through the notes. Today shouldn't be too difficult. We're talking about graphs, which you guys are pretty familiar with how to use the graphing calculator, and then you're pretty familiar with some of the terminology that's used, like domain and range and end behavior and stuff like that. So anyways, we'll get to that in just a few minutes. But first, let me go through last night's homework assignment with you. Here's number 2. Again, remember yesterday we talked how we have to get this radical isolated. So I need to move that 15. So that will leave me with the square root of 4k minus 11 equals 2 minus 15 is negative 13. So now that I've got this thing isolated, remember our next step is to get rid of that radical. So we raise both sides to the power of the root. And in this case, this is the square root. So I need to raise both of these sides to the second power. On the left side, of course, this is going to cancel, and it's going to leave me with 4k minus 11. But on the right side, negative 13 times negative 13 is positive 169. So I'm going to solve the problem old school. Like this is just way back when you guys solved linear equations way back in the day. We're going to add 11. So 4k will equal 180. And then we're going to divide by 4. And 180 divided by 4 is 45. So I've gone through my whole process correctly. Now I got to just check to see if 45 truly does work. So I'm going to go to my calculator, and I'm simply going to type in the square root of 4 times 45 minus 11. Then I'm going to scroll outside of that radical and do plus 15. And we're going to see if that in fact does equal 2. So again, just straight in my calculator, I'm going to type this in. The square root of 4 times 45 minus 11. I'm going to scroll outside of that and put my plus 15. And in this case, I get 28. Now, 28 definitely does not equal 2. So this is one of those cases where the solution that I get, even though I went through a whole process correctly, the solution is extraneous. Extraneous solution. Okay? So that's number 2. Here's number 4. I've already got worked out. Take a moment to see if what you did was correct. I'll talk you through it real quick. I added 11 to isolate this radical. I know it's written as a rational exponent, but we talked about how that's the same thing as a radical yesterday. So I added 11, got 6. Then I got rid of that rational exponent by raising it to the power of the root squared. See that? It cancels it. So 6 squared equals 36. This x plus 7 comes out. I solved by subtracting 7, and there it is, 29. I went back and I plugged it in, and sure enough, it gave me negative 5. Well, negative 5 equals negative 5, so that one is a solution. Okay, number 6. Again, I'm trying to isolate this radical right there. So the first thing I need to move away from is a 17, and I do so by subtracting. So negative 2 times the square root of 3x plus 10 will equal 1 minus 17, negative 16. Then, of course, I got to get rid of that negative 2 as well. So I'm going to divide both sides by negative 2. This will cancel, leaving me the square root of 3x plus 10 equals 8. Okay, now we're ready to go ahead and get rid of this radical here. And we do so by raising it to the power of the root. And that root is 2, square root. So that's what I'm going to do. I'm going to square both sides. So that will cancel on the left. So 3x plus 10 will equal 8 squared, 64. And then my process from here is old school. I subtract 10. So 3x equals 54. And then I divide by 3 So x equals 18. Okay, done. Now I go back up to the original problem and I type it in. 17 minus 2 times the square root of 3 times 18 plus 10. And I see if it equals 1. So here I go. I'm going to go to my calculator and type it in just like I see it. 17 minus 2 times the square root of 3 times 18 plus 10. So just like I see it, I enter it and I get a 1. So let's go back to our paper. Well, 1 definitely equals 1. This is a true statement. Therefore, 18 is my answer. It is not extraneous. Okay? So pretty easy. Here's number 8. Already worked out. Both of these were in, they're raised to rational exponents. So technically, they are radical equations. So we get rid of those by raising it to the power of the root. Well, the denominator of a rational exponent is a root. So we cube both these. Cancel, and I'm left with just 3x minus 21 equals 19 minus x. Real simple. Then I got my x's together first by adding x, 4x. Then I added 21, 40. Then I divided by 4, x equals 10. I plugged it in, and perfect. It's exact match. Okay? Moving along to number 10. Again, I want to work this one out. Some people will see this divided by 2, and that'll freak them out a little bit. Well, most of the time, we don't like working when we're dealing with fractions at all. And what do we do to get rid of divided by 2? Well, we multiply by 2. So what I did personally instead, just so I didn't have to work with this fraction, I multiplied by 2, and it left me with the fourth root of 7w minus 5 equals 2 times the fourth root of w minus 2. Now, why would I do that? Well, because now there's no fraction involved. But think about it. I really can't do anything with that 2 currently because I've got these radicals on both sides. And that 2, again, if I move it over, I'm just back to where I started. So I'm ready at this point to take both sides and raise them to the power of the root, which is 4. On the left side, since the only thing over there is the fourth root and whatever's underneath it, those will cancel, and 7w minus 5 comes out. But this right side, remember, we had a problem like this yesterday. That 2 is not inside the radical. So that 2 has to be raised to the fourth power. It doesn't just get to cancel out. 2 has to be raised to the fourth power. And 2 raised to the fourth power is 16. Now, that's being multiplied by the fourth root of w minus 2 to the fourth power. Now, that is going to cancel, and w minus 2 pops out just like we see it. Now, if you look at this problem now, well, yeah, I need to distribute that 16. So 7w minus 5 equals 16w, and then 16 times negative 2 minus 32. So let's solve this thing. I'm going to move this 7w over by subtracting it. So negative 5 will equal 9w minus 32. Now I'm going to add 32. So negative 5 plus 32 is positive 27, and that equals 9w. Divide by 9, w equals 3. So let's go check that. Let's go see if that's right. I'm going to go back to my original problem. Let me erase all that so you know you are reminded of what it looked like. I'm going to go back to my original equation, and I'm going to type into the left side the fourth root of 7 times 3 minus 5 in the numerator divided by 2. And I'm going to check to see if that's equal to the fourth root of 3 minus 2. I'm just plugging this value of 3 into the w on both sides, and I'm going to check to see if they're equal. So here we do the first one. I've got a fraction, so alpha y equals number 1. Up top, we got fourth root of, so 4 math 5. We talked about that. And then I do 7 times 3 minus 5 up top divided by 2. And sure enough, that equals 1. Now I'm going to do the other side. 4 math 5. And then it's just 3 minus 2, which is also 1. So let me go back to my paper. And sure enough, 1 does equal 1. Therefore, W does equal 3. So hopefully you guys understood that. It's not too hard, but it does have some challenges. So here's number 12. Number 12 was a lot like number 12 actually yesterday, except instead of having square root of 12 minus n, we have 12 minus n to the 1/2. Same thing. Remember, the denominator is the root. So we square both sides. And then actually, it's a lot like yesterday's because the factors are the same. N plus 4 times n minus 3 will give me this n squared plus n minus 12. So I set these both equal to 0. Both of them I tried the negative 4 here, as you can see. It gives me negative 4 equals positive 4. Nope, not true. So negative 4 is extraneous. I plug the 3 in here, and sure enough, 3 equals 3. It works. Okay, let me do one more, and then we'll go into today's notes after I go through the last example. Number 14 was a lot like 14. I think it was 14 on the review. I can't remember what problem it was. Doesn't really matter. But here's what we're going to do. This radical here is isolated. And there's nothing I can really simplify over here with c plus 4. I can't move anything around, so I'm ready to solve this thing. And I do so by raising both sides to the power of the root, square root. So I square both sides. Now, on the left side, that 6c plus 15 gets to pop out of that radical, escapes. But that c plus 4 needs to be multiplied. So here we go. 6c plus 15 will equal c times c, c squared. C times positive 4, 4c. 4 times c, 4c. And 4 times 4, positive 16. Now I'm going to combine all my like terms, so I'm going to subtract this 6c over here to these c's. I'm going to subtract this 15 right underneath the 16, and these will cancel, and sure enough, 0 will equal c squared. 4c plus 4c is 8c minus 6c is 2c, and then plus 1. Again, if I'd have recognized this, I probably would have changed the problems I gave you. Sure enough, this one factors exactly like the homework did, or the notes. C times c gives me c squared. To multiply to get a positive, it's either both positive, both negative. I look right here, both positive. And sure enough, just like our example that we did yesterday, again, that's kind of a I didn't realize it was going to mess up like that. But anyways, 1 times 1 will multiply to get 1, combine to get 2. So I only have to take c plus 1 and set it equal to 0. When I solve that, I subtract 1. So c equals negative 1. Now, real quickly, I'm going to go back to the original. Let me erase it to make sure I remember what the original looked like. And I'm going to type in the square root of 6 times negative 1 plus 15 on one side. And the other side, I'm going to type in negative 1 plus 4, which I really don't have to type that in. I know that's positive 3. But anyways, let's do the other one. We got the square root of 6 times negative 1 plus 15. And it equals 3. So just like the right side, the left side equals 3. So 3 equals 3. It works. Therefore, this is my solution. And there you have it. Now, the last one, again, 5th and 6th period, you guys, or 4th and 5th period, you guys weren't given this problem. But 1st through 3rd, you were. You can check it. This was a lot like the last example that we did in class, but we didn't quite make it to 4th and 5th. But here you have the solution. It was a little bit more challenging. So the answer was 25, but when I go plug 25 back in, it doesn't work. So look real quickly at that as you start transitioning, as you're done, over to your other paper, the notes that you were just given, that's stapled with the homework attached as well. We're going to jump right into that. Okay? So I'm going to get my calculator out. I'm going to go ahead and reset this thing. I always like resetting it because we're about to do some graphing. So let's flip over. And again, if you have some questions from this homework assignment, hold on to them, because as I told you guys all yesterday in class, Wednesday is going to be used to clean up any struggles that you maybe had on either that homework assignment or tonight's. So let's get started with tonight's, and hopefully you won't have any struggles, but if you do, on Wednesday we'll cover that. And then also remember what I put on the board. I'll give you a quiz review that you can start working on in class on on Wednesday, hopefully. Thursday, you'll get to watch a video of this review being just taught, and then Friday you'll take your quiz. Okay, here we go. We're going to first start with graphing a square root function. A square root function would simply be f of x equals a square root of x. This is what we call the parent function, meaning there's been zero transformations whatsoever. Nothing has happened to change where this thing starts, which direction it goes, if it's vertically stretched or vertically compressed or anything like that. Reflections, nothing. This is the simplest form of a square root function. So let's look at what the simplest form of a square root function looks like. So I go to y equals, and I do the square root of x. Just real simple. So I want you to notice, where does that thing start? Right on the origin. So what I'm going to do, instead of trying to find points here, I'm going to go to my table, and I want you to notice something. Remember how I just said it starts at 0, 0? Well, look what happens if I go below 0 on the x-axis. All these are errors. Why? Well, it doesn't go any further on the y-axis than 0. So I'm going to start graphing a couple of these points. I'm going to find some nice ones. Here's a nice one. 0, 0. Go ahead and go put that on your graph. Here's a good one. 1, 1. There's a good one. 4, 2. So 1, 2, 3, 4. 1, 2. And let's see if there's any more that are halfway decent points between before 10. Let's scroll down a little bit, and there it is. 9, 3. 9, 3. So again, I'm going to go back to my graph, and sure enough, notice this thing starts right at your origin, and it just kind of curls up and to the right. It curls up and to the right. So let's name some things that you're pretty familiar with. 1, endpoint. Where did this thing start? Well, it started right at the origin. Why? Well, it hadn't shifted left. It hadn't shifted right. It started right on the origin. Here's some more things that you need to know. The domain. Remember, domain is what can x equal. Now, think about this, guys. Can the graph come way over here? Well, of course not. It starts right at the x value 0. Now, how far will this thing go to the right? Well, it's going to keep on going right and up gradually forever. So the domain is from 0 to infinity. How about the range? Does the range ever go below 0? Of course not. So my range never goes below 0. That's the minimum. But it goes up and to the right forever. So the domain and range are both 0 to infinity. Again, I used a bracket on the 0 because that's truly where it started. So that's what a square root function looks like. Let's move now into a cube root function. A cube root function. Now, before I talk about a cube root function and why it's going to be different, I want you to kind of have a logical understanding of y. Why is this graph just this? Well, because remember, guys, if x went negative, am I allowed to have a negative in a radical, in a square root? No. So that's why everything to the left of 0, -1, -2. When you go look at that table, everything to the left of 0 was undefined because you can't take the square root of a negative. It's not definable the way we define values. But is that going to happen in cube root functions? I mean, remember, you can have positives and negatives. So cube root functions are going to look different. So I'm going to do that. I'm going to go to math, number 4, and do the cube root of x and see if we were right. Yeah, absolutely we were right. So it never stops going left or right, never stops going down or up, but I still want to get some points. So if I look at my table, you're going to see some points. You've got 0, 0. You got -1, -1. You've got +1, +1. I'm graphing these, y'all, as I go. I'm going to scroll up a little bit. I've got -8, -2. And would anybody like to guess what another one would be that would fit on here? Hopefully you see that this is a mirror image. +8, +2. So let me go back over here to my graph and show you what this looks like. Instead of this right here being a endpoint, see, it doesn't end there. It's what we call a turning point. So that's the point at which it curves. So this thing's making its way up. It curves upward, and then it curves right again, and then it keeps on making its way up and to the right. So that turning point is still at 0, 0. Why? Well, it hasn't shifted left. It hasn't shifted right. That's what moves the turning point. Domain. Think about how easy domain is for a cubic function, a cube root function. It never stops going left. It never stops going right. So domain is unlimited. -infinity to +infinity. This thing never stops going down. It's gradual, but it's still going down. It never stops going up. It's gradual, but it's always going up. So my range is also unlimited. So there you have it. These are the basic graphs of square root and cube root functions. But sometimes these graphs make transformations. They move around. They get steeper. They get flatter. They go to the left. They go to the right. They go up. They go down. They got all kinds of things they reflect. They got all kinds of things they could do. Transformations. So let's remind you guys of what these transformations are. When we deal with a square or cube root function, that value on the outside, that thing that you're multiplying by on the outside, will tell you the two things that we've needed to know for a while. One, if A is negative, then that function is going to vertically reflect. That means it's going to reflect over the x-axis. Let me go back up here. So for example, what I mean by that, if this turned negative out in front of here, this thing's going to flip right over this x-axis, so it would be down here like this. That's what it would be doing. Same with this one, okay? If A out front is negative, that thing's going to reflect over the x-axis. Well, remember the other rules about this number? If this value out here, not the negative sign, not positive, negative, but if the value itself is greater than 1, that thing is vertically going to stretch. It's going to get steeper. It's getting pulled upwards, and that's going to cause it to be go up a little higher. But remember, if that value is between 0 and 1, so if it's like 1/3 or 3/4 or 1/2, that thing is going to vertically compress. It's going to flatten. Okay? Now, remember the stuff that happens on the inside always represents horizontal change. If it's being added or subtracted, it's horizontal shift. And hopefully, guys, remember that on the inside, it works the opposite. So if H is positive, well, let's start here. H represents that horizontal shift. And if that H is positive, that thing's going to shift. Remember, it means it's actually negative. It'll shift to the left. But if that H is negative, remember that means it's actually positive, it's going to shift to the right. So it'll always do the opposite on the inside. But notice where that K is located, y'all. That K is outside. Outside means vertical. So we're being added or subtracted on the outside. That's going to be a vertical shift. And remember the rule, it is what it is. So positive means up and negative means down. Hopefully you guys remember that. Those are the shifts that we're going to talk about. Remember, the end point or the turning point will be where that thing has shifted. So it'll be your HK value. Okay? That'll be your endpoint. So let's talk about the transformations. We're going to compare these to the parent function. The parent function for this one is the square root of x. Let me just write it. The square root of x. So what's happened to this thing? Well, remember, on the inside, that's horizontal shift. And it looks like a -7, so that means it's a +7 horizontal shift. So it shifts right 7. And then remember, outside is vertical, and it is what it is. So that's a +2 vertical shift. So it shifts up 2. Pretty simple. I hope you guys all agree. Okay, this one. The parent function here is clearly the cube root of x. So what all's going on? Well, it's being multiplied by 4. Well, 4, guys, is way greater than 1. So 4 is going to represent a horizontal stretch. Whoa, what did I say? Not horizontal stretch, a vertical stretch. And then, of course, that -1, where does it happen? Outside. Vertical shift. Vertical shift. And remember what we said about vertical shift? It is what it is. So -1 means that it shifts down 1. Okay, moving on to the next one. Again, you can notice, hopefully, this is a cube root of x function. So clearly, I have a negative. What's that mean? It's going to reflect over x axis, vertical reflection. Then this is happening inside, that's horizontal shift. Remember the rule? If it looks positive, it's actually a negative horizontal shift. So it shifts left 3. I hope you were thinking that in your head. Okay, moving on to number 4. Again, notice what the parent function is. It's simply the square root of x. So all the changes have been made to the square root of x. What's this first one? Well, we're multiplying by a number that's between 0 and 1. That's a vertical what? Compression. This thing's getting flattened. Then this is your horizontal shift. Remember, if it looks negative, it's actually a +2 horizontal shift. So it shifts right 2. And then this out here is your vertical shift, and it is what it is. So -6 means it shifts down 6. Okay? All right, moving along. Now we've got a couple of problems that ask us to do the exact opposite direction. Okay, now they're giving you guys your function. See, this is square root. Look, it says square root parent function. So we got the square root of x. And they want me to do all these things. reflect it across the x-axis. Well, where do I represent reflection across the x-axis? Well, that's a negative out in front. Then it shifted 7 units left. Guys, where does horizontal shift happen? Inside. Now 7 units left, I think -7. But remember, on the inside, it's the opposite. So instead of it being -7, it's actually +7. And then it says 1 unit down. That's vertical shift. That happens outside. And remember the rule? It is what it is. So 1 down means -1. So there you have it. There's a function that has all of those pieces to the puzzle. Okay, look at the next one. It says cube root function. So I know I'm dealing with the cube root of x. Let's see all the stuff. It says that it has a turning point located at -2, +3. Remember, that's h. Okay, that's your horizontal shift. Remember how that works? If it's a -2, what will it actually look like in here? +2. And if that k looks positive, remember, it will be the same out here, so +3. And there's anything else? Nope, that's it. So there's my function. So hopefully you guys understand transformations. So we're going to end this lesson with a couple of graphs. I'm going to do 2 of them. I'm going to do 2. So which ones should I do? I'm going to do 8 and 9. I'm going to skip number 7 because that one's way too easy. Let's look at number 8 and 9. Okay, number 8. Let's go type in. Actually, you know what? On my paper, and you're going to do this too. Hopefully you're all paying attention. I want you to change this to the cube root. The cube root of x minus 1 minus 4. So make that change real quick. Now we're ready to go graph it. So here we go. Let's go to y equals. I'm going to clear out what we got in there. And we're going to do the cube root. So math number 4, the cube root of x minus 1, then scroll outside the radical and do -4. So let's graph this thing. Let's see what's happened. See, remember the turning point, or the turning point is usually on the origin. This thing is definitely shifted down and to the right here. See it? So where did it shift? Well, go back and look. You know. It shifted right 1, down 4. So my turning point is right 1, so +1, and then down 4, -4. So that's my turning point. Why is it called a turning point? Because that is not an end point. It keeps on going. So let's go back and find some nice points. So let's go put 1, -4 right in the center. And I've got, there's my turning point, 1, -4. I've got 0, -5. I've got 2, -3. Let's go see if we can find another one this direction that fits. There's one. 9, -2. And let's go back to the other way. Let's try to find one more good one that fits. There it is. -7, -6. Okay, I think I got them all right. Let's go see if our graphs look the same. So I've marked those points, and sure enough, it looks pretty good. This thing starts down low. It's going up and to the right. It curls through that turning point. Then it goes up and then starts making its way up and to the right. So there's the graph. Okay, let's answer a couple questions. Domain range. Remember, on cube root functions, that's easy. Never stops going left, never stops going right. So my domain is unlimited. My range never stops going down. I know it's gradual, but it's going down. It never stops going up. So my range is unlimited. Okay, so that's easy stuff. Increasing interval versus decreasing. I'm gonna skip over this in behavior real quick. Increasing, decreasing intervals. Think about this. with cube root or square root functions, it's never going to do both. It's going to do one or the other. So this one, look, it's always doing what from left to right? It's always going up. Look, it's going up flat, flat. It's going up steeper, but still always going up. So it's increasing for the life of the graph. It's never decreasing. Not applicable. Okay? Put a line through there. I don't care. It can only be one or the other. Now, in behavior, remember how this works? As x approaches infinity. What's that mean? As x is going off to the right, what's y doing? Well, it's going up. I know it's gradually, but it is always going up as it moves to the right. But what about as x goes to the left? As we go to the left, isn't it always going down? So there you have it. There's my end behavior. Again, these are words that you're all familiar with. So it should be something that you can do, no problems. Now let's go to number 9. And I'm going to go, actually, you know what? Before I go to that, let's find our endpoint or our turning point. Now, whether you know whether it's the endpoint or turning point, yeah, it doesn't matter. You know that your HK is your endpoint or your turning point. So remember, if that looks like a +1 on the inside, what does it actually mean? It means it's a -1. And what's your K value out here? There's nothing being added or subtracted. It's 0. Now, which one is it? Is it endpoint or turning point? Well, it's all about the root. That's square root. Square root's going to be an endpoint. That's where it's going to start. So let's go see if that's right. Let's go to y equals. Let's clear this thing out. Let's do 3 times the square root of x plus 1. That's all there is to it. So I graph it. And sure enough, did the endpoint move to -1, 0? Well, I know I can't see. It looks like it stops. And I don't know why it's doing that. I actually think if I zoomed in, let me see. I think if I zoomed in, I don't know why it's showing that way. And let me show you why. Let me go back to Zoom Standard. If I go to my table, does it give me -1, 0 as a solution? Yeah. So I'm not sure why it's doing that on the graph, but -1, 0 is the endpoint. Now look where it goes from there. It goes up to 0, 3. See how steep it's going? Then it goes to 1, 2, 3, 1, 2, 3, 4, 5, 6. And that's pretty good, but let's see if there's another one on here. Yeah, there's one, 8, 9. 8, 9. And that's all I can fit on here. So look, here's my graph. This thing starts right here, and it goes up real steep compared to the others. Why? Well, look, it was vertically stretched. That value out there is a 3. So let's talk about domain. Domain. What's the x value right here that it cannot go past? -1. Now, it can go right forever. So your domain is from -1 to infinity. Okay, now let's reverse that. What's the y value it cannot go past? Well, it cannot go past 0. Look, it can't go past 0. It can go up forever, so it can go towards infinity, but it cannot go past 0. So there you have it. There's your domain. Whoops, I meant to erase. There's your domain and your range. Last 2 questions in behavior. As x goes to the right, what's y doing? It's going up. And then this one's a little trickier. As x is going to the left, what's it doing? As x approaches negative infinity, what's it doing? Well, can you say that f of x is going down? Well, not really, because it's only going down for a while. Right? Look, it's gonna stop going down. So how long will it stop going down? Well, it can't go down below what y value? Because remember, f of x means y. It's going down, but it can't go down past the y value 0. So as f of x looks or moves to the left, f of x is approaching 0. And it cannot go past that point. I hope you understand that, because that generally tricks people. That's probably the trickiest thing about these. This is probably one that you'll hold on to ask me about. But anyhow, notice the other thing I said that was true above. As we move from left to right, what is this thing always doing? It's always increasing. With square root and cube root functions, it will be either or. It can't be both. It's going to be one or the other. So it is increasing always, but where did it start increasing? It started increasing as it left -1. See, we're going with x, the x value -1, and it started increasing from there forever. And there is no decreasing interval. It's only always going up. So that is how you graph square root functions. Now this video right now is at 40 minutes and 46 seconds, so you don't have a ton of time. So you can't really do much in class, but here is the assignment. You've got your graphing calculators on your calculator. You've got Desmos. You've got Calculate, whatever. If you don't like, there's all kinds of good options to graph these. So here's your homework. I want you to do 1, 2, 3, and 4 on the front. Also, I want you to do number 6 on the front. And then we're going to do on the back number 8 and number 10. Number 8 and number 10. Okay? So that's your assignment. 1, 2, 3, 4, 6, 8, 10. Okay? That's only 1, 2, that's 4, 5, 6, 7 problems. So shouldn't be too hard. So remember, if you have any questions, either about last night's homework or about these graphing functions, I will be back with you on Wednesday, and I will spend class time going over any questions that you have. I do expect that you guys work on this and give it your best effort. There's no reason that you can't do this. It's easy stuff. You have graphing calculators. If you don't, that's on you, because you know that they're available on your smartphones. If you don't have a smartphone, you have a computer that you can access at home, and Desmos is always there. All right, so thank you guys. I hope that you paid attention, and I'll see you tomorrow.